Hello everyone, and welcome to some more remote learning. Today we're going to do a little bit more with Taylor series and just talk about representing real numbers with Taylor series, which we've been doing all this time without actually physically plugging in numbers for x. Now if you remember back to all of our last section stuff, so that last chapter where we were just figuring out whether series converged or diverged, there were only two series that we could figure out if they did converge, what they converged to. And that was the geometric series and a telescoping series. But now with these Taylor series, we can actually figure out what that infinite sum actually goes to. So what it converges to, and we can get that value that it converges. So when we know that it converges, we'll be able to figure out exactly what it converges to. So I just have one example for this worksheet, but we're gonna really work through every step, kind of reviewing a whole bunch of parts from this section. So in example 1, it says to write the Maclaurin series for f of x equals the ln of 1 plus x and find the interval of convergence. We're going to start with that step, and then we're going to evaluate f of negative 1/2 to find that value of the series 1 over k times 2 to the k. Yes, you can use your table of common Taylor series because the book tells us exactly what this is. It lists out the first couple of terms and then that series. And that table will also tell us the interval of convergence for the ln of 1 plus x. However, I said I really wanted to review this, so we're going to start from scratch. So if our f of x is the ln of 1 plus x, then how do we find that Maclaurin series? Remember, we have that pattern, right? We have some c sub k, which we're going to define, and then times x minus a to the k. For a Maclaurin series, what's that a value? That a value is equal to 0 for a Maclaurin series. So when writing out our Taylor series representation, we're going to have f of a, which is f of 0, plus f prime of 0 times x minus a, which is x minus 0. So x plus the second derivative at 0 all over 2 factorial times x minus 0, which is again just x squared, plus the triple derivative or the third derivative at 0 over 3 factorial times x cubed, and so on. Now I think it's useful to make a quick table to help us figure out f of 0, f prime of 0, and the rest of those derivatives. So this is going to represent my function, and my next column will represent that derivative at 0. So without taking the derivative, we have the ln of 1 plus x, which we know the ln of 1 plus x, if we're plugging in 0, is the ln of 1, which equals 0. Now taking the derivative of the ln of 1 plus x, that's 1 over 1 plus x. So plugging in 0 for x, we're going to get 1 for that derivative. Now, taking the derivative of that, this is like 1 plus x to the negative 1. So now we're going to have a negative 1 over 1 plus x squared. What's that going to give us? That's going to give us a negative 1. Taking the derivative of that, that's a negative 1 plus x to the negative 2, so that becomes a positive 2 over 1 plus x cubed, which 1 plus 0 cubed is 1 cubed, 2 over 1 is 2. So let's give this pattern a go. F of 0 we know is 0, so we're going to plug 0 in, and then we're going to add that to f prime of 0, which is 1, so that'll be 1 times x, plus, although look at this, that derivative is actually negative, so I'll subtract 1 over 2 factorial times x squared, and then I'm adding, because that next derivative is positive, 2 over 3 factorial times x cubed, and it's still a little hard to see the pattern, so while we're at it, why don't we just take one more derivative. So let's do the derivative of 2 over 1 plus x cubed. That's like 2 times 1 plus x to the negative 3, so that becomes a negative 6 over 1 plus x to the fourth. So plugging in 0, I'm going to get negative 6 over 1, which is a negative 6. So now I know that I'm going to be subtracting, this will be 6 over 4 factorial times x to the fourth. And this pattern continues on. So I can't really pick up 1 over 2 factorial, 2 over 3 factorial, 6 over 4 factorial. I can't necessarily pick that pattern up, so I'm going to try simplifying to see if it becomes more clear. So this 0 essentially goes away. So I'll have 1x, or x, minus x squared over 2, because 2 factorial is 2, plus, if I took 2 over 3 factorial, that's 2 over 6, which is 1/3, so plus x cubed over 3. Then I'm subtracting 6 over 4 factorial, that's 6 divided by 24, which is 1/4, so that'll be x to the fourth over 4. And there we go. Now we have a clear pattern. This is all going to equal the summation from, as opposed to starting at a k value of 0, since that first term went away, I'm going to start at a k value of 1. So we're going to have x to the k in our numerator, and that's going to be all over k, because x is over 1, then x squared is over 2, then x cubed is over 3. So that's x to the k over a k, but remember, I'm oscillating, starting at a positive to a negative, positive to a negative. So I have negative 1 to the, now if I want my first term to be positive, I don't want negative 1 to the k, because that would be a negative 1. So I'll want negative 1 to the k plus 1. And there we have it. Go ahead and confirm with your table. The Maclaurin series for the ln of 1 plus x is the summation from k equals 1 to infinity of negative 1 to the k plus 1 times x to the k all over k. So we have our series representation, but we don't know when it's actually equivalent to that function. When this series is equivalent to the ln of 1 plus x, that's for x values that make the series converge. So we need to figure out what x values will make this series converge. And we can do this by either the root or the ratio test. Let's go ahead and do the ratio test. And I'll circle my series that we're doing that ratio test on. So remember the ratio test. I'm not going to go too in depth with this because we should have done this multiple times in these examples now. But I'll talk you through it. It's the limit as k approaches infinity of a sub k plus 1 over a sub k. Now this negative 1 to the k plus 1, because I'm taking that absolute value sign, it's not really going to affect my problem. So I'm going to leave that negative 1 to the k plus 1 out for the sake of time. So this will be x to the k plus 1 all over k plus 1. And that gets multiplied by the reciprocal of a sub k, because I'm dividing by a sub k. So that'll be k over x to the k. Now I can rewrite this limit, simplifying this numerator, because x to the k plus 1 is x to the k times x, that's multiplied by k, all over k plus 1 times x to the k. Now you'll see that my x to the k's cancel out, which, if we're taking the limit as k approaches infinity, I can pull that absolute value of x out in front. So I get the absolute value of x times the limit as k approaches infinity of k over k plus 1. And k over k plus 1, highest power rule, that limit goes to 1. So overall, my limit for the ratio test, I get the absolute value of x. Now remember, I did the ratio test. When does the ratio test converge? When that limit is less than 1. So when my absolute value of x is less than 1, I'm converging. So I know for a fact that that's going to be between x values of negative 1 and 1. I know I'm converging for all values in between that. However, I don't know what's happening at those actual values. I don't know what's happening at negative 1, and I don't know what's happening at 1. So this is where we're going to test our endpoints. So like I said, this video is going to be an overall review of a couple of different things that we've previously learned, getting into representing that real number, really hitting this power series stuff home. And so let's continue on and review testing the endpoints. So remember, this number line represents my x values. So in order to figure out if I'm converging at -1 or converging at 1, I'm going to take those x values and plug them back into my original series. I'll start with testing -1. So we have the summation from k equals 1 to infinity of -1 to the k plus 1 times -1 to the k all over k. Well, if I simplified that series down, I'll get the summation from k equals 1 to infinity of, well, I can combine my -1 to the k with my other -1 to the k to get a +1 to the k multiplied by, well, this -1 to the k plus 1, when I split it up, was -1 to the k, which I combined with this -1 to the k, but I still have a -1 to the 1. So that'll be multiplied by a -1, and that's all over k. Now 1 to the k is just 1. So this is going to be the summation from k equals 1 to infinity of -1 over k. Now remember these sum rules, I can pull that negative out in front because it's just a constant. So what do I have here? I have a p series, right? What's the value of p for my p series? My p value is equal to 1. So I actually have the harmonic series, which with that p value of 1 for the p series, we know this diverges. So we are indeed leaving an open circle at -1. Because we diverge when x is equal to -1, -1 is not included in our interval of convergence. Now to test our next endpoint, I'll go ahead and switch up the color. Let's test the summation from k equals 1 to infinity of, we're no longer plugging in a -1 for x, we're plugging in a +1 for x. So that'll be -1 to the k plus 1 times 1 to the k all over k. So this, when we simplify it down, is equal to the series -1 to the k plus 1 is -1 to the k times -1. So writing this out, we get -1 to the k times -1 times 1 to the k. Combining 1 to the k with -1 to the k, we still are going to get a -1 to the k, because -1 times 1 is a -1, and that's all over k. So the difference between these two series, when I plugged in a -1, I just had a simple p series. But pulling this -1 out in front, when I plugged in my +1, I now have an alternating series. So I need to do the alternating series test to see if I'm converging or diverging. So I'm going to do the alternating series test where my a sub k is 1 over k. Because remember, when we're doing the alternating series test, we're looking at that absolute value as our a sub k. And our first step for the alternating series test is to show that it's non-increasing, which there's a few ways of doing that. I think one of the easiest ones is to take the derivative. If the derivative's negative, then we're set, because that means our overall series is decreasing. So looking at 1 over k, taking the derivative of, well, essentially k to the -1, so I'll write this out. Taking the derivative of 1 over k will become -k to the -2, which is indeed negative. So check, we are non-increasing. And then the next step is to show that the limit as k approaches infinity of that a sub k, so the limit as k approaches infinity of 1 over k, goes towards 0, which it does. So by the alternating series test, this series, because it meets the criteria for 1 and 2, we know that this series converges. That's why it's important to test the endpoints. So even though we weren't converging at a -1, we are indeed converging at +1. So this circle will get filled in. So our interval of convergence is -1 is less than x, which is less than or equal to 1. That's our interval of convergence. And again, go ahead and confirm with that table. All of this information that we just worked through was already in our table, but I thought it was important to review how to get there so that we understand each of these steps. So from here, we're saying that as long as x is between -1 and 1, so including that +1, then our series is going to be equal to the function. So we're going to actually know what that infinite sum is equal to, as long as x falls within that interval of convergence. So now we can jump into actually representing that real number, where it says evaluate f of -1/2 to find the value of that infinite sum. And I'll give you a hint, we're going to use everything we just found. So let's go ahead and consolidate all of this information just to make it a little bit easier to understand. And so that we still have the word problem up here, I am going to erase all of this work. So again, f of x was the ln of 1 plus x. And we found that that was equal to the summation from k equals 1 to infinity of -1 to the k plus 1 times x to the k all over k for the interval from -1, which is less than x, which is less than or equal to a +1. This is all the information we just found out by finding that Maclaurin series representation. However, now we're going to evaluate f of -1/2. So think about it. We're going to do f of -1/2, which is equal to the ln of 1 plus a -1/2 or 1 minus 1/2. That's going to equal, remember, we're just plugging in -1/2 in for x. So from k equals 1 to infinity of -1 to the k plus 1 times -1/2 to the k all over k. So simplifying that down, what do we get? We get the summation from k equals 1 to infinity of -1 to the k plus 1, that's -1 to the k, times -1 times -1/2 to the k all over k, right? Well, let's simplify that down a little bit more. That's going to be the summation from k equals 1 to infinity of -1 to the k times -1/2 to the k is going to be a +1/2 to the k, which I can write as 1 to the k over 2 to the k, or 1 over 2 to the k. So that's where I get 1 over k times 2 to the k. Now this -1, I'll just pull that out in front. So you can see, we can easily find this value because the ln of 1 minus 1/2 is the ln of a +1/2. And the ln of a +1/2, if we were to actually do that math out, is a -0.6931. So the negative value of this series converges, and it converges to -0.6931. Or the positive side of that will converge to that positive decimal. So not only do we know that this series converges because that x was indeed between -1 and 1, but we know the exact value that that series converges to, which is that -0.6931, or if we were looking at the positive of this series, we would need a positive 0.6931. So hopefully this video helped tie everything together. We started with our basic formula for a Taylor series to build that into finding our Maclaurin series, so an a value of 0. Then we found that interval of convergence. We also had to test our endpoints in this example, and we were actually able to evaluate that function to get the number that that series represents. So I think this is all really cool because now we know what that infinite sum of numbers, which would take us forever to figure out, we know the exact value that that infinite sum is equal to, which is pretty awesome. So hopefully that clears up questions for power series, Taylor series, Maclaurin series, and gave you a little taste of all the different things we've done. So hopefully this was overall a good review. If you have any remaining lingering questions, feel free to leave them in the comments below. Good luck and see you next video.